Hey guys, welcome back to my channel. Today's video, let's talk about one question asked by one of my students on B side. The question is here. So what are the relationship differences, connections between coefficient of determination, which is r squared, correlation coefficient, which is Pearson's r, and I also add another one measure, is the regression coefficient B1, because I think this measure B1 is also related to the other measures, especially related to correlation coefficient, Pearson's R. Okay, so three measures will be talked about in today's video. One is R squared, and the other is Pearson's R, correlation coefficient, and the third one is regression coefficient, which is B1. Okay, so hope this can help you better prepare for your final exam. Okay, so without further ado, let's get into the video. Let's talk about the difference in connections between coefficient of determination, which is r squared, correlation coefficient, which is Pearson's R, and regression coefficient, which is B1. Okay, so first, coefficient determination. It's actually r squared, so official name of r squared is the coefficient determination. The reason we call it r squared because r squared just equals Pearson's R squared. Pearson's R and then squared, you get r squared. So Pearson's R is actually correlation coefficient. I've spoken a lot of r squared. So r squared is actually the fraction of total variation in y that is accounted for or explained by the regression model. So that's sum of squares, the model, divided by sum of squares total. Let's suppose we have the linear regression y equals b0 plus b1 x and plus error. And you want to know why there is variation in y. And you use x to explain y. Without any regressor, so you only look at the values of y, right? You have a data like this. You have the data y1, y2, y3, y4. Without any explanatory variable, you just look at this data, this your observed data. You can easily solve for sum squares total. That's total variation in y. We said that variation is actually sum squared of something. So each value minus average of y. So that's y1 minus average of y. You can easily compute that squared plus all the way to y sub n, the last value of y minus y bar squared. So that's what we call the sum of squares total. Sum of square total is actually the denominator here. And the sum square model is variation in y explained by the model. So you have the variable x, you're using x to explain y, x1, x2, right? And use x to explain y. You see this is a predictive value of y, right? If you know OLS regression, you know that this is a predictive value of y, and this error includes all the unobserved determinants of y, right? So now sum of squares model, right, equals sum, use x, you can get the predicted value of y for each observation. It has nothing to do with observed value of y. So this y hat is only determined by the value of x. So when x equals x1, you plug that into here, you solve for the predicted value of y, right, y1 hat. And then the difference between y1 observed value and y1 hat is estimation error, right, something you can't explain, or that we call this variation depends on the other determinants of y, or some unobserved determinants of y is in error term. But you want to look at what the variation in y explained by the model, just use y hat minus y bar squared. So these two y bars are the same. So based on the value of x, you have y hat, you can generate a predicted value of y hat 1, y hat 2, all the way to y hat n. And use each value of y, subtract average of y. So that actually equals y hat 1 minus y bar squared, all the way to y hat sub n minus y bar squared. And then the rest of the variation is sum squares error, right? So that's sum error squared. So that's for each observation you have observed value of y minus predicted value of y and squared. So that's sum square error. So basically sum square model plus sum square error equals sum square total. Again, this total variation in y, explained by the model, variation in y explained by the error. So r squared is just the the fraction of total variation in y explained by the model. Okay, so let me write here. So it's just a fraction or percentage of total variation in y that is explained or accounted for by x or by the model. The model is b0 plus b1x. Right, this is the model. So this is r squared. So Pearson's r is just a correlation coefficient. Let me remember right here. So Pearson's r squared, and Pearson's r is just a correlation coefficient. So that's if you want to find the relationship between two variables. What's important to know about Pearson's r is that the Pearson's r has no directional causation associated with it. So what I mean by that, so you see, if you're writing this equation b0 plus b1x plus error, that means you assume that the direction of causation is this direction, or you're using x to explain y, or x causes y, or the value of y depends on x. Right? This is what we call this direction of causation. Right? If you write this equation like this, right? b0 plus b1y plus error, and now that means you assume that you use y to explain x. We call this reverse causation. Pearson's r doesn't matter which variable is your explanatory variable, which variable is your dependent variable. So Pearson's r just give you the correlation between two variables. So that's why correlation coefficient, we just use CORR, right? Correlation coefficient is denoted by CORR of x and y, or correlation coefficient between the variable x and y equals correlation coefficient between y and x. It doesn't matter which variable goes first, no direction of correlation associated with this measure. Equals 0, that means there's no correlation. You can write this yx, 0 correlation, that changing x associated with nothing changing expected value of y. Or you can write this way, this is y, this is x, changing y associated with nothing changing x, because there's no correlation. You know that there's no correlation between x and y. It doesn't matter which variable is independent variable, which variable is dependent variable. Okay, and if this is greater than 0, that means x goes up, y goes up, like x, y move in the same direction. X take on a larger value and y also take on a larger value. Or if this is a x and this is y, like this, x goes up, y goes up. If this is less than 0, goes the two variables have negative correlation. So that's y, x smaller, y greater, right? Same thing. This is a y, this is x, like this. By convention or rule of thumb is if the correlation coefficient absolute value, right, between x and y, if this is greater than or equal to 0.7, we call this, we say that they have strong correlation between each other because it can take on negative value, so we use absolute value, right? The correlation coefficient between x and y, if this is greater than or equal to 0.3, less than 0.7, normally we say they have a moderate correlation. So if this correlation coefficient between x and y is less than 0.3, we call this weak correlation. Okay, so now let me give you the Pearson's r's correlation coefficient, the mathematical expression, so or formula. So that's sum x minus x bar times y minus y bar, right, this is a variable sum, divided by standard deviation of x times standard deviation of y. Assume we have large samples, so I just ignore degrees of freedom here. You see there's no, so x and y in this formula seems like symmetrical, right? X and y. So there's no, you can't tell any direction of causation or any direction of causation, any importance of one variable over the other. So it's like x minus x bar, y minus y bar, x standard deviation of x, standard deviation of y. It's like x and y are totally symmetrical, right, in terms of importance. Again, you can't tell any direction of the relationship here. So we call this Pearson's r. Again, r squared, right? R squared is a fraction of variation of y explained by x, is actually the Pearson's r squared. Let me just zoom out. So this r squared is just Pearson's r squared. This r squared is Pearson's r squared. Okay, and the third measure I want to mention today is not mentioned in that question. The question only asked me the relationship or the difference between coefficient of determination and correlation coefficient. I think there's one more measure is also relevant here. So let me write here. So third one is regression coefficient. So now let me give you the regression. B0 plus B1x plus error. So here, this B1 is called regression coefficient, or coefficient of the regression, or coefficient of x, right? So this B1, you see this B1, how to interpret B1? The change in y for a unit change in x, right? So x increased by 1 unit, how much change in y? So y, suppose is positive, increased by B1 unit, right? So you see, there is a direction associated with this measure. So y tells us the effect of x on y. So if you write this equation like this, b0 plus b1y plus error, and now you interpret b1 as the effect of y on x, right? So this effect x on y. By convention, we always use y to denote dependent variable, x to denote independent variable. Okay, so there's a direction. So now you're using x to explain y. So there's a directional causation here. So now what is B1? So B1 is very much related to Pearson's R. So but now instead of the symmetrical relationship between x and y, so B1 has is different. So you will see from the formula B1 how different x is from y. So that's sum, they have the same numerator. So x minus x bar values of y minus y bar, same numerator, but denominator is sx times sx, or standard deviation of x times standard deviation of x, or you can also write this way, divided by sum x minus x bar squared. So you see, same numerator, numerator of coefficient of regression equals numerator of Pearson's R. But Pearson's R, because there's no direction of causation, so we have standard deviation of x times standard deviation of y. But this B1, because there's a direction, right? You're using x to explain y, so the denominator just the variance of x, right? So, and now you can tell the difference or the relationship, right, between Pearson's R to B1. So you can write this way, B1, the regression coefficient equals Pearson's R, the correlation coefficient between x and y, times standard deviation of y over standard deviation of x. You see, so this times standard deviation of y over standard deviation of x, and then you can cancel out the standard deviation of y, and the denominator turn out to be a variance of x, right, same as here. Okay, so that's a relationship between coefficient regression B1 and Pearson's R. You see, because standard deviation of y greater than 0, larger than 0, so this whole thing always positive. So that means B1, this B1, right, this B1 always had the same sign as Pearson's R. If Pearson's R 0, B1 0, right, because denominator can be 0. Right? Numerator 0, numerator 0. If Pearson's R is 0, B1 equals 0. If B1 is 0, Pearson's R equals 0. If R is positive, B1 is positive. R is negative, B1 is negative, but they have different magnitude, right? Different magnitude. So R and B1 could be a different value, but they have the same sign. Okay, and different interpretation, right? Because this is just use x to explain y, and here there's just a correlation, right? Correlation coefficient between two variables. So now let me highlight the measures. One is r squared, fraction of total variation of y explained by x, that actually equals Pearson's R squared. And Pearson's R is like this. X and y is symmetrical or have the same importance here. We're not using x to explain y or y to explain x. Right? This is Pearson's R. Let me write here. And the third measure is this. Right? We call this regression coefficient. And the relationship between regression coefficient and Pearson's R is like this. Okay, same sign but different magnitude. Yeah, this is for today's video. Hope you find today's video helpful. Any other questions, comments, concerns, confusions regarding statistics, econometrics, and micro-macro theory, please feel free to let me know. Comment down below or send me messages. Really appreciate all your participations. Thank you so much. Okay, thank you so much for watching, and see you next time. Bye.